Hi students, welcome to another video on this love circuits. So in this video we'll see the working of ADC, the timing diagram and the related issues. Let us start with the block diagram representation of ADC, which stands for analog to digital converter. So as we know that it is an analog to digital converter, so we are supposed to give an input which is analog in nature. When I say analog in nature, so it can be having any amplitude that can be keep varying with respect to time. So now suppose if you want to find, okay, this is the input voltage, so I want to find its digital equivalent at a given point of time. So at time t is equal to t1, I'm having an amplitude of some v1 here. So at some other time, okay, t2. So at time t2, I have a different amplitude v2. So and of course, so I may have an amplitude maybe at around t3. So it is some other amplitude. So now, unlike in your DAC where we are given some digital input, zeros and ones, we are getting the output voltage. So for that you have to give the digital input, you have to wait until I get the output. But here, since your input voltages keep changing, you have to say when for which input voltage you have to convert you have to find the digital equivalent of that analog voltage. So now for that this ADC requires an input called as start. So when to start the conversion. So another input that is required is start input. So start is an input that is to be given to the ADC to initiate the conversion. Start is one more pin. And of course, we will going to learn in the detailed block diagram. So there is a clock required. So there is one more input that is required. This is clock. This is clock. This indicates that this is a edge triggered clock. So this is a positive edge triggered clock. This is also an input, and this ADC will give a indication that conversion is over. So that's what is an output. This we call it as end of conversion. End of conversion, which is given in abbreviation as EOC, end of conversion. So now you have the analog input voltage whose analog voltage will be digitized. So that's what is one of the input. The other input is when to start the conversion, that is start, and there is a input required for the clock which is inside the ADC. We're going to have a counter, so that's what is it requires a clock. And after the end of conversion, it will give an indication that the conversion is done. Once the conversion is done, the output will be in the form of digital output, which will be n bit. It will be n bit. So this is digital output. So it will be of n bit. Now this is a typical block diagram indicating there is an input and there is an output which is digital output, which is of n bit. For all these things, it requires a reference voltage, which we'll call it as V reference voltage. And of course, the supply voltage, all those things are separately required. Suppose if we go to the detailed block diagram of this ADC, so we have something like DAC based ADC. DAC based ADC. So as the name itself indicates that in this ADC, there is a digital to analog converter. Suppose if you consider, so this is my input signal that is given to a comparator. This is my the input voltage, which whose this can be minus or this. Of course, this is interchangeable. You can change it, and that is going to a counter. This is a counter, and I'll have counter come controller. This is not simply a counter, this also controls when to allow this start of conversion, when to make this clock to allow this, when to give this EOC signal, all those things. So this is end of conversion, This is start, you can say this is input, this is output, and you have the digital counter output. Counter is a what digital counter. So let me say it as B1, B2 goes like this up to Bn. Let me say this as LSB, this is MSB. So that will be given as the input to the DAC. So this is digital to analog converter, and this will give a output voltage. That output is compared with the input, because we know that input for the DAC is the digital input coming from the counter, and this DAC requires a reference voltage, and this will be the output what you are looking at. So this is B1, B2 up to Bn. This is my output. This is output, this is input, and this is DAC sounds. Okay, this is clock. Of course, you know the working of this. So as long as this DAC output is less than input voltage, this counter is allowed to count, and this will be keep updating. So once this DAC output becomes slightly greater than input voltage, it stops the counter. Then there's a EOC generated, and you can read the output from this digital output. So for that, what is required is you need to have a continuous clock. So it is, let me just indicate, instead of writing hundreds of clock, let me just break this clock somewhere here. So this break indicate that in between that I have got a lot of cycles. This is my clock. This is start. So I will give a start pulse. So once I give the start pulse, this is having so many cycles, and then end of conversion is okay. Now whenever it is in the conversion mode, the output, the EOC goes low. Whenever conversion is completed, EOC goes high. So now this is the point where we are saying that conversion is okay. Maybe in some textbook, so the conversion starts from here itself. The conversion starts from once you give the start, but the effective conversion time starts from where you are ending your start signal to where does your this EOC goes high. This is T conversion. So after this EOC goes high, this is an indication that conversion is over now. Now from here I can read the data. Once your conversion goes high. This is your clock. It takes n number of it takes so many clock cycles. In case of this counter based a DAC based counter, which is a normal counter, it takes okay, if the amplitude of the input voltage is more, it takes longer more number of clock pulses to give the output. If the input voltage is less, then it takes lesser count to give the output voltage. That's why the EOC in such case of ADCs will depend on the input amplitude. The conversion time depends on what is the magnitude of the input voltage. If Vin is less, then T conversion is also less. If Vin is more, then the conversion time is also more. So this is what is the conversion time. So you have to write this comparator, this counter come controller, start signal, clock, EOC. You can see start is going in, clock is also going in, EOC is coming out. The output of the counter is going to the input of the DAC. V reference is a reference voltage required for the DAC. So you have an output voltage coming from the DAC that is compared with input. So as long as V0 is less than Vin, so this is keep on counting up. So once the V0 becomes slightly more than this, then counter stops. You can now read the output. So this requires a clock, a start of conversion, and end of conversion is this your conversion time. Now similarly, we can think of another DAC, which is nothing but successive approximation DAC. This is SCA ADC, successive approximation ADC. This is similar to the DAC based ADC. Only difference is that the counter will not be a normal counter, but it is a counter starts with making MSBS high. With making MSBS high, we simply call it as SA register. SA register, meaning that successive approximation register. So here also you have this B1, B2, B3 going up to Bn, which is the earlier as we wrote it here. It is B1, B2, B3. This is considered to be MSB. This is LSB. This is Bn, which is now LSB. You can take a tapping from here. You can take a tapping. It is B1, B2, B3. So many dots. This is DAC. This is your V reference, and you have your, this is SA register come controller. There is a clock, there is a EOC, it's an output, and there is a start. There is a start signal, and you have a comparator which allows this SA register to change the state depending on, okay, now this is of course this can be plus minus, this is V in. Of course, you know the operation of this SA register. The bit will be retained as high, or it will be discarded to 0, and then the further subsequent bit will be made high. That's what the process. I'll not go to the details of the SA register. You initially make B1, B2, B3. If it is 8-bit, you can write it as B4, B5, B6, B7, B8. So this has got a weight of 5 by 2, 5 by 4, 5 by 8, 5 by 16, 5 by 32, 5 by 64, 5 by 128, 5 by 256. So initially, of course, you can reset everything. Then once you are starting, it is this is your bit. So you have a digital, this is your digital input for this DAC. So you have a corresponding output voltage V0. So that V0 will be 2.5 volt. You compare that with this input. If this 2.5 is less than this, then you retain this and you make the other bit as high, and then do it. Suppose whatever voltage that you get here, if it is more than that, then you have to discard this, make this 101, and continue till all the bits are covered. So now you can see since you're starting from this till the last bit as 1, the conversion time remains the same. So whereas in case of previous DAC based ADC, conversion time was depending on the amplitude of the input. If the amplitude was less, the conversion time was happening earlier, the conversion time was less. So but in this case of successive approximation type of ADC, again you're going to have a clock. Okay, those who are done ADC using 0808 might have seen that it takes 64 clock cycles to complete the operation, independent of the amplitude of the input voltage. So whatever the frequency of the signal is, it takes typically 64 clock cycles. So this is my clock. You give a startup conversion. So once your startup conversion is done, the EVO, of course, I just make a break. The EOC starts, and then it will be there till 64 clock cycles. Then it goes up. So from here to here is your T conversion. So for ADC IC, which is 0808, this is 64 cycles. Meaning if the clock frequency is 640 kilohertz, then T conversion is typically 100 microsecond. This is your data sheet information. It can happen even by 96 microsecond, or it can take 116 microsecond as the longest time and the least time. So typically it is 100 microsecond. Matlab it takes 64 clock cycles at a frequency of 640 kilohertz. So whenever you do any DAC operation, sorry, any ADC operation, write the block diagram, write this start and EOC, and write the conversion time, so that will be a complete package like for a ADC. So just writing this block diagram will not give a good in-depth analysis into the ADC. Now just want to let me just touch upon triple five timer, a stable multivibrator and monostable multivibrator very quickly. So now I want to generate a stable multivibrator for a square wave, a free running oscillator using triple five timer. So this is VCC. I will have a reset pin. So there is an output pin, there is a control voltage, there is a ground pin, there is a trigger pin, there is a threshold pin, and there is a discharge pin. This is if you want to write the pin numbers. So this is pin number 8, pin number 4, pin number 3, pin number 5. This is pin number 1, pin number 2, this is pin number 6, this is pin number 7. This is a triple five pin. Let me write the circuit diagram. This is connected to plus VCC, and we have one resistor here, another resistor here, and one more resistor here. Let me just connect it to ground. Let me have a capacitor connected to this. This is CS stabilizing capacitor. Let me ground, let me short this threshold and trigger, give it to this junction. Let me connect this to this. Let me have a diode bypassing this. This is now R1, R2, CT. The purpose of having this diode is now I'm intentionally making this capacitor to charge to VCC through this. So this is my charging part. This is my charging part. The discharging part is this. The discharging part is through this. So this is charging part, green one. Discharging part is this. So now what is tau charge? That is RC time constant is R1 into CT. What is tau discharge? Tau discharge is R2 into CT, because it is a timing capacitor. Through R1 it charges, through R2 it discharges. So now, of course, you all know the timing diagram of this. So I say this is on time. This is, I can just make the duty cycle very small also, very high. Now this is a large duty cycle. This is what is happening. This is with respect to time. This is V0. I can write. This is going up to VTH. We'll go up to VTL. This is VTH. This is VTL. This is T on. T off. This is VTL. This is VTH. So VTH is equal to control voltage. Control voltage. The control voltage is usually 2/3 of VCC if you're not connecting anything here. This is control voltage, which is 2/3 of VCC. VTL is always half of VTH, which is nothing but 1/3 of VCC. 1/3 of VCC. So now, to find, okay, you have a capacitor equation. TC of T is nothing but V final minus V initial e power minus T by RC. So upon substituting for T is equal to T on, the R is equal to R1, the C is equal to CT. So now what is V final? V final is equal to VCC. This is VCC. V initial is VTL, and VC at T on is equal to VTH. If you substitute all these things, you'll get the expression for T on as R1 CT ln of VCC minus VTL by VCC minus VTH. This is the expression what we want to get. So now this can be 2/3 of ACC, or if you don't have this, suppose you connect a battery here. If you connect a battery here which is V reference, so then VTH is equal to V reference and VTL is equal to half of V reference. Half of V reference. That's what is here. Whatever VTL is there, VTL will be 1/3 of VCC and VTH is 2/3 of AC if you're not connecting a reference voltage. If you connect a reference voltage, then VTL is half of V reference, VTH is V reference. So it is as simple as that. So this is the expression for TR. To find an expression for TR, you can see I'm writing only R1 because while charging it is bypassing R2, so it is not passing through R2. If you take out this diode, then it passes through R2. I'm just making a very generalized circuit. Using this, you can get whatever duty cycle, 10%, 90%, 95%, 12%, 66%, whatever percent you want. So you can just realize it using this. So for finding T off, if T is equal to T off, then R is equal to R2, C is equal to CT. I'm just talking about this RC, this RC. What is V final? V final will be 0, V initial will be VTH, and voltage at VC of T off will be equal to VTL. Upon substituting all these things, you'll get the expression for T off. T off will be, it is R2 CT ln of VTH by VTL. This will be always 2 because this is always half of this, so that this expression for T off invariably it is R2 CT into ln of 2 is 0.693. This will not change even when you have a reference voltage or when you don't have an external reference voltage. Even if you are running the capacitor, the T off expression is this. Even if you have a reference voltage, T off expression will not change, whereas the T on expression depends on what is the voltage at control voltage. Hope you got this what I'm talking about. So this is called as a stable multivator because the output voltage is neither stable in this state 1 nor stable in state 0 here. So this is keep changing from 1 to 0, 0 to 1. As soon as the capacitor voltage reaches exceeds VTH, it comes down. As soon as it goes below VTH, it again goes up. This is a stable multi-vibrator. Next, moving on to monostable multivibrator. Monostable multivibrator, which has got a stable state, and you have to move the circuit out of that state for a temporary state. So this is VCC basic discharge. You have threshold, you have trigger, you have ground, this is control voltage, this output. This is number 8, 4, 7, 6, 2, 1, 5. You can have a capacitor here. This is grounded, this is output. This is capacitor. This is discharge and this is my trigger signal. Trigger signal should be something like that, so that you can able to apply a trigger signal going less than VTL. So this is CT RT. This is CS. This is the output. Now this is your trigger signal. Let it initially high. You make this to go low and then let it go again high. So you can just give one more trigger signal after some. This is V trigger. V trigger. This is the create as DCC V0 volt. We have a level called as VTL. This is my time V0. So as long as your trigger is high, the output is in state of 0. This is now stable state. Stable state. Output goes to quasi stable state. It remains in this quasi stable for a predefined time. It again comes down and then it again goes only when there is a trigger is applied. It just comes back here. This is what is T pulse width. So during this time the capacitor will charge from 0 to VTH and then come down to 0. This is 0 to VTH. This is VTH. If you don't connect any external power supply, then VTH is equal to 2/3 of only condition that the trigger signal should go less than VTL, then only it is called as a stable state. So now you again have the same expression of Vc of t is equal to V final minus V initial, V final minus V initial e power minus t by Rc. So what is R and C? R and C is this RTCT. V final is VCC, that's what is this voltage VCC. V initial is this, it is again VCC minus 0 e power minus t pulse width by RTC. So this is not V final. So what is the voltage at t is equal to t on it is VTH. So it is VTH is equal to, this is VF is V final, V initial is 0. If you solve for this, T pulse width becomes RT CT ln of VCC divided by VCC minus VTH. So this is a voltage. If VTH is equal to 2/3 of VCC, then T pulse width is equal to RT CT ln of 3, which will be 1.09 times RT CT is the pulse width, provided you are not applying any voltage. Suppose if you apply some X source here, then this will be 5 volts, whatever VCC divided by VCC minus this voltage. So this is your V. So then this VTH will become or V reference voltage. This is about the monostable multi-outlet. So it, of course, this is going to VCC. This is grounded. This is trigger. The output voltage is in stable state of 0 volt. As long as you are not giving any trigger signal, the trigger signal goes below VTL, output goes sign, stays there in the quasi stable state of VCC. CB of capacitor voltage is just VTH. VTH can be 2/3 VCC or VTH can be the control voltage which is being externally supplied. The expression for the pulse width is 1.1 RT. So this is close to 1.1. So where this is RT, this is CT. Hope okay, this will going to help you in realizing the pulse width of desired dimension. Thank you.